Hello, this is Isaiah Crowe showing you my project, project number 4, I believe. Yes, project number 4. I'm doing just part 2, A through C. Starting out, open the thing. I only used geometry, mesh, and setup. Didn't end up needing solution or results. So, starting with geometry, this is my shape. I did it about, I believe it's 10, what was that, 10 meters? I believe it's 10 meters by 5 meters. 2 meters. 10 meters by 2 meters. Here's my 1 meter diameter semicircle. Put it at the front because I thought I was going to do more wake stuff, but I didn't end up. You will still see a lot more wake stuff on my graphs though. Now moving over from geometry to mesh. Mesh, I did it very different from the other times. Because I found that the rectilinear or the quadrilateral just didn't work right. So what I did instead was honestly quadrilateral might still have worked. The main difference I did was that I did an edge sizing from the border of the circle a certain distance out with inflation. So I did the edge sizing, and then in order to get this like circle you see around it, that'll actually make it us able to get any values there. I used inflation, setting it to 0.003 or something like that. I forget what this actually equates to. But with 25 layers and some growth rate, I think that's just the normal growth rate. And that gave us this nice uniform. Oh, this nice uniform shape right here. And then this doesn't matter too much except for contours, which makes it fine that it's also disorganized. This is just what needs to be organized. Naming selections, obviously set velocity inlet, pressure outlet, the walls, and then the cylinder that makes them. That is the most important. Yeah, that's about everything for that portion. Now I did everything else in here. Did not have to go into solution like I normally do. Was just able to do everything in setup. First thing, set it to standard K epsilon here. Then air, I set the density to 1.2. Then in, I believe, reference values. No, something before. Yes, reference value. Computing from the velocity inlet, we have 30 meters per second. As you can see, density is still the same. And the reference zone is the surface base, which I don't see a picture of right now. But let's see if I can pull up what it looks like. Do I have to close both of these? No, I think I just open a different window, right? Is this full screen? No, I'm not sure, but you'll see in a second when I open up the graphs. Boundary conditions. This was setting the velocity inlet. Then initialized and ran the calculations. Let's just run it. Sure. Bam, 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 bam. Okay. Yeah, I don't see. There's normally a place where you can switch between graphs and other stuff. Don't know what that is. Dismiss that. Scale residuals. Skablam. And then on to part 1, part A. Get velocity contours and streamlines, and then pressure contours. Okay, velocity contour is the first one. Save and display. Skablam! It looks beautiful, doesn't it? Absolutely beautiful. And this looks great, especially you can see that nice, let me actually open up the path lines. Display. Nope, that's not what I need to do. Display. Add to. Bam. Bam. There we go. Skablam. Velocity streamlines. You can see it's very high velocity here as it gets pushed against the plate, which means there'll be low pressure there as well. Low velocity here, which means there'll be high pressure. Gonna be high pressure there, I believe. And then meow. All of those lines going there. I know it's definitely gonna be high pressure there. But I believe it may also be high pressure. It might also be low pressure there, actually. Let us check. Now going on to pressure. This is medium pressure there, actually. But yeah, as you can see, very low pressure here because the velocity is so high, it's not running into anything. High pressure here because it just slams into it and stops. This is the static pressure, by the way. Dynamic pressure. Skablam! Look at it, it's beautiful. High there because it's the dynamic pressure, so it's going to match up with the velocity. You can see this nice area right here where it has the wake. You can see the nice wake right there. Contour number 4. Bam! It's the total pressure. So obviously all of this should be equal because dynamic plus total should just, dynamic plus static should just be total. So all of that's the same. And here in the wake region, it gets messed up here, obviously, because the shape is impeding it. We got a beautiful lake, the prettiest wake I ever seen. That's all the contours. Now over to the velocity graphs. That's everything for A. Now for number B, plot the pressure coefficient and velocity distribution. Okay, pressure coefficient. Save and plot. Here's here's the pressure coefficient, as you can see, going along the cylinder wall. Starting high, going low, and then into the wake region, where it evens out. Then velocity distribution. This one is weird. It's all 0. I believe this is because of the no slip condition. Because this is asking for the velocity distribution over the surface of the cylinder, it's just 0 because of the no slip condition. As soon as it hits it, the velocity just becomes 0. I would show you the graph again, but yeah, so it's 0 because I believe right here, right up against it, velocity you can see becomes 0. No matter what, even in the really high velocity area, it becomes 0 right there along the edge. So if it asks for the velocity distribution of this whole area right here, like, I don't know, like 0.5 meters out from the circle, it would be very different. It would be an actual pretty looking graph. But because it's just along the surface, everything is just that. And so you get just a line. The final thing, I did it through, where was it? I forget exactly what I went through. Report definitions, I believe. Is that right? Yeah, new force report. Did drag and then lift. You can see them down here. Oh, I guess they disappeared, so I'll just do them again. Force report. Drag. Over the cylinder wall. Compute. And it appears down here. It's not a graph or anything. It's just this value. This is for part C. Number C. Get the drag and lift coefficient for the semicircular cylinder from Fluent and tabulate the results. I don't know what tabulate the results means. Am I supposed to get like multiple drag and lift coefficients and then graph them? But I don't see how that is possible, seeing as when I ask it for along the wall, it just gives me 1. So unless this is somehow the average, which I don't think that's how that works for coefficients. So this is just what I got. I put that into the project for the answers because I don't see a way to tabulate it per se. This is just what is given to us when we ask for the coefficient over the cylinder wall. And then of course, asking for the lift is the same exact thing. Over the cylinder wall, compute. And it gives you it right here. Coefficient of lift over the cylinder wall is 1.31, which seems relatively accurate. Same with this. Yeah, and that should be everything for it. I took the screenshots of everything, put them in here. Bam, 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 bam. So that should be everything for this project. If I was supposed to graph it somehow, then sorry, I didn't really know what this meant, honestly. I'm assuming tabulate the results just means export it, like, or not export, but like just, I don't know, this must mean tabulate. I'll ask my teammates though, because they're also tabulating results for the Reynolds number. Because yeah, it wasn't like for all cases, it was just to drag a lift. Okay, anyway, that should be everything for my project. My favorite part was this beautiful, beautiful wake, bro. Well, actually, my favorite wake was that beautiful, beautiful wake. Absolutely exquisite. Absolutely looks great. Nah, actually, never mind. This is my favorite. This is the best graph. This velocity graph looks so good. Okay, and that